All right, so we're jumping from 4.2 to 4.5. So 4.3 is a L'Hopital. We're not covering that. It's not part of this class. And 4.4 talks about analyzing one more time. So 4.4 is not a bad section. It talks about analyzing one more time, but it adds oblique asymptotes. We don't need to cover oblique asymptotes. You do need to know horizontal asymptotes and vertical asymptotes. So we're skipping 4.4. It's just like 4.2, but they throw in asymptotes. We do not have to do oblique asymptotes. You do need to remember how to find a vertical and how to find a horizontal asymptotes, which was on the last test. Okay, so we jump to section 4.5. 4.5 is absolute max and absolute min. What is that? So a function has a local max where the function is less than or equal to f of c at x near c, and a local minimum if f of x is greater than f of c for x near c. In this section, we seek the largest and smallest values of f of x throughout the domain of the f. Bottom line is absolute max is the highest point in the entire graph. It's the highest max, but it's the highest point in the entire graph. Absolute min is the lowest point in the entire graph. It's the lowest min, but again, the lowest point in the entire graph. So the definition about absolute max and absolute min, if f of c is greater than or equal to f of x for all x in the domain of f, then f of c is called the absolute max of f. If f of c is less than or equal to f of x for all x in the domain of x, then f of c is called the absolute min of x. But again, we'll give you some concrete visuals and explanations. So an absolute max or absolute min is called an absolute extreme. Okay? So let's say we're looking at this graph. We're going to just look at graphs. We'll do work later, but now we're just going to kind of look. If I look at the function x cubed over 3 minus 4x, notice the graph goes up, the graph goes down, the graph goes up. Okay? Do we have a local max? Do we have a local max? Where's the local max? About? Negative 2.5. Is everybody clear that that's a local max? Just by looking at it. No work. Just looking at the original, that's a local max. Okay? Do we have a local min? Where's the local min? 2, negative 5. What this section is all about, you're probably like, that's all? Yeah, that's really what it's about, is it an absolute max? Yes, it's a local max, but is it an absolute max? In order to be an absolute max, you have to be the highest point in the entire graph. So we're agreed that that's a local max. But is it an absolute max? Is it the highest point in the entire graph? And the answer is no. And the reason why it's no is, what does this arrow mean? It goes up forever. So is this point higher than that? No. So it's not an absolute max. Is this an absolute min? No. Why not? The graph goes down forever. So you may be thinking, oh, it's the lowest of the lows. It's the lowest point in the entire graph to be an absolute. Okay? And again, we're just going to look at some pictures to begin with. So in this case, there is no absolute max or minimum. We have a local max and a local min, but we don't have an absolute max or min. Okay? Now let's look at this graph. We have a graph of 4 minus x squared. 4 minus x squared. Do we have a local max? Where is it? 0.4. Are we okay? Do we have a local min? Nope. Just by looking at the original, we know that. Is this an absolute max? Is it the highest point in the entire graph? Yep. There's no points higher. Nothing's going higher. In this case, we have an absolute max. Okay? It has an absolute max. We do not have an absolute or local min. Okay? Let's look at this graph. This is a graph of x to the 2/3. Just by looking at it, do we have a max or a min? We have a minimum at 0, 0. The question is it an absolute minimum or is it a local minimum? Absolute minimum. Why? It's the lowest point in the entire graph. There's no points any lower. That's it. Okay? So theorem 1 says a function f is continuous on a closed interval a to b has both an absolute max and an absolute minimum on the interval. So if I give you a domain, and I've already mentioned it ahead of time, that the three things you need to look for is take the first derivative, set it equal to 0, look at the first derivative if it's undefined, and then the third thing, see if there's a domain, an interval. Those could also be maxes or mins. They throw it in here in 4, 5. So if you had the function x to the third minus 21x squared plus 135x minus 170 on the interval of 2 to 12, okay, let's do this one. So take out a piece of paper. I want you to find the maxes and mins of that function. After we do it, we'll talk about it as an absolute or a local. But this is a review of section 4.1. Take the first derivative, set it equal to 0. At least get started. I'm going to give you a head start. I'll teach it, but I'm giving you a head start. Find the extrema of this function. Find the extrema of this function. This is going to show me, are you studying along the way, or you're learning it, forgetting about it? You've got to be studying along the way. Find the extreme. Okay, so I want to give you a head start because you're going to find out where you get stuck is not anything to do with the extrema. So for the extrema, you take the first derivative, which is 3x squared minus 42x plus 135, and set it equal to 0. Set it equal to 0. Okay? And then you're going to find out, the problem that I may have is, not that I don't know how to take the first derivative, it may be what? Factoring. So let me give you a couple reminders, okay? Number one, is this quadratic? If it's quadratic, what could we use? Quadratic formulas. So I hit program, quad form, A is 3, B is negative 42, C is 135. And am I looking for solutions or vertex? Solutions. So you get 5 and 9. So if you sat there waiting for me to go over it because you don't know how to factor, guess what? Factoring is your problem. That's the issue. Now, I will tell you, since my solutions are nice answers, will this factor nicely? Yeah, it will. So if you were able to factor it, you would have probably pulled out the 3 first, which would have left you with x squared minus 14x plus 45. And then you would have factored x, what two numbers multiply to 45 but add to 14?
5 and 9.
Minus 5, minus 9. Then set each piece equal to 0. You get x equals 5. X equals 9. Now let me stop here, okay? Again, I gave you a head start, not because I want to review extrema again, it's because your problem is factoring. And if you had a problem right now, you'll have a problem on the assessments, right? Because factoring is one of the things you have to know. And if you don't know how to factor, yeah, you have the quadratic formula as a backup, but we need to get the factoring down, okay? But I also want to review extrema. When you check for extrema, you should be checking 3 things, okay? Number 1, take the first derivative, set equal to 0, solve. Any questions there? The next thing, look at the first derivative. Is there any number that could make this undefined? Am I dividing by anything? Am I doing anything weird like that? Nope, so there's nothing undefined. And then the third thing, which I've mentioned before, but is finally showing up in the notes, is you look for any endpoints. Where would the endpoints come from? The domain. So because it tells me we start at 2 and we end at 12, I also need to check 2 and I need to check 12. So the third thing that I've been kind of foreshadowing ahead of time is endpoints. That comes from the domain. That's the new part today, in addition to absolute compared to local limits. Are we okay? Yep.
Sorry, might lay down a little bit. Where'd you get the 2 and 12 from?
That's given in the problem.
Okay.
Just given. So you don't have to worry about finding it or solving it or anything like that. Okay? Now, stop there. Any questions? Now, if I want to know where these points are, we've been making a table. So the points I'm concerned with are 5, 9, 2, and 12. And where do I plug them in? First derivative, second derivative, or original? Original. So let's plug those points into the original. Why the original? It's because all of this is about the original. It's about the original. It's finding the extrema of the original. So let's go to y equals, type in x raised to the 3rd minus 21x squared plus 135x minus 170. So y1 is the original, and then we plug in the numbers that we found, 5, 9, 2, and 12. So 5 gives us 105. 9 gives us 73. 2 gives us 24. And 12 gives us 154. Okay, stop there. Now, do we have maxes, mins, all that stuff? Do we have all that? And the answer is, I don't know. I don't know if we have maxes, mins, all that stuff. How will I find out? Graphing. Now, here's the deal. Yes, you need to know factoring. Yes, you need to know derivatives, but you also need to know how to get an appropriate window. But we have a huge clue. The clue is the graph begins to exist at 2 and ends to exist at 12. Does everyone understand what this means? So when I graph, what's my x-axis going to be? 2 to 12. So that domain is telling me my graph begins at 2 and ends at 12. Nothing exists before 2, nothing exists after 12. That's where my graph begins to exist, is at 2, and it ends existing at 12. That's what a domain is.
So you would want to do it like certain 14?
Not at all, because a domain means where it begins to exist and where it ends. So I don't want the cushion this time, because I'm not looking for a point. This tells me where it begins to and ends to exist. Okay? Now, they don't tell me the range. So to figure that out, I look at my y's. What would be an appropriate y to see from 24 to 154? What would be an appropriate window? You could start at 20 and go to 160, but we want to get some good cushion. So I'd maybe go from like 0 to 160, or maybe 0 to even 200. Give yourself some cushion. Give yourself some cushion. So for the y, let's go from 0, maybe all the way up to 200, counting by 50s. Now again, Nobody's going to give you the window. No one will give you the window. Where do you get the window from? The X comes from the domain, and the Y comes from what you want to see. So we may have to change it, but let's do this for now. Window, 2 to 12, counting by twos. 0 to 200, counting by 50s. So we make a window appropriate. We're graphing the original. And we'll label all our points. So we have 5, 105, 9, 73, 2, 24, and 12, 154. Now that I have a picture, I'm going to ask you to label each one. And I want you to label it as local max, local min, absolute max, absolute min, or neither. Now that you have a picture, label each point. Local max, local min, absolute max, absolute min, or neither. Okay, so let's look. 5105, what would we call this point here? A local max. Good. It's not an absolute max because it's not the highest point in the entire graph. What about 973? What would that be? Local min. It's not the lowest point, but it's a min. What about 224? That's an absolute min. And then what about 12, 154? Absolute max. Okay, so in section 4.5, what are we adding? We're adding, don't forget to check the endpoints, and we're adding the difference between a local max and an absolute max. Local max, absolute max. Are we okay? And if you're a little confused maybe on this one saying, is that a max or a min? The definition, a quick definition of a max is left and right or lower. If left and right are lower, therefore it's a max. If I don't have a right side, if the left is lower, it must be a max. You have to climb up to it. Same thing, this is a min. The right is lower, I have to walk down to it. Are we okay? Questions? That's essentially 4.85. And then here's the graph that they have. Now, they're going to repeat this a couple times. We already did the work. I just want you to kind of look up. And let's say the domain was 4 to 10. Okay? So we can go to our calculator and change, instead of 2 to 12, but 4 to 10. That's what we would do by hand. But here's what they have. Okay? If we changed it to 4 to 10, now the graph has changed. Would 4 be an absolute, local, max, min, or neither? What would this one be? This would be a local min. Okay? Now again, we're only talking about the blue part here now. What would this point be? Forget about the dotted, that's the old graph. Just look at the solid blue. What would this point be now at 5? That would be a what? Absolute max. Why? It's the highest point. This says isn't here. Actually, maybe let's do it in the calculator. Maybe you need to see your own. Okay? So let's go to the calculator. There's a little dotted line messing this up. They're saying, what if the domain was not 2 to 12? What if the domain was 4 to 10? So change it from 4 to 10, 4 to 10. Change it from 4 to 10. And now the graph changed. Okay? If I hit second trace value 4, which is right here, is a local min because it's not the lowest. 5 is now going to be an absolute max. Why? Because now we're only seeing this much. It's the highest point in the entire graph. That becomes an absolute max. What about 9? What does 9 become? Absolute minimum. It becomes the lowest point in the entire graph now. And then what about 10? What does 10 become? A local max. It is not the highest max. It's just a local max now. Okay? So if I go back to the graph on the slide, remember, this is what it used to be. This is what it is now. And if you look at those points, this would be a local min. This would be an absolute max at 5105. This would be an absolute min at 973. And at 10, this would be a local max. Yep.
So when would it be neither?
Neither is if, like this point right here, where it's on its way down, that would be a neither. Because it's not a max nor a min. Because remember, this process, first derivative, set it to 0, look at the first derivative for undefined endpoints. These are possible extrema, doesn't mean they are for sure. You have to check to see what they are. So if there was something here, that would be a neither. Okay? Now, they're just going to keep messing with the domain. So if it was 4 to 8 now, and let's look at our graph. So if we change the window from 4 to 8, if we change the window from 4 to 8 now, now we're only looking at this portion here. We're only looking at this portion here. So if I did second trace value 4, this would be at 4, this would be a local minimum. Local minimum. At 5, we would have a absolute max. And at 8 now, we would have an absolute minimum. Absolute minimum. The lowest point in the entire graph. So when I go back to their graph, again, only the solid blue line now. Local min, absolute max, absolute min. Are we okay? What makes it an absolute min? It is the lowest point in the entire graph. What makes that an absolute max? It is the highest point in the entire graph. We okay? So just a lot more examples. And again, if we, same example, they just went from 3 to 11 now. They open it up 3 to 11. So if I go to my graph, make it 3 to 11. Okay, so from 3 to 11 now, second trace value 3, what do we have at 3? Now, it looks like an absolute minimum, but you may be wondering what this one is. You may be wondering what that one is. So let's look at 9. 3 is 3,73. Is that a min or a max? Minimum. 9 is 9,73. Is that a min or a max? Min. So here's the question. They're both min, and they're both the lowest. They're both min, and they're both the lowest. So would they be local mins or absolute mins? Can you have more than one absolute? The answer is yes. So are they local mins or absolute mins? Absolute mins. You can have more than one. They are both the lowest. They are both the lowest. Okay? Let's look at 5, 5,105, and 11,105. 5,105, 11, 105, what would they both be? Absolute maxes. Absolute maxes. Okay? So what we're learning is the difference between a local and a max, and you can't have more than one max. You can't have more than one max. Absolute max and absolute min. Okay? So theorem 2, how do you find local absolute extrema? Absolute extrema, if they exist, must occur at a critical number or at endpoints. So just like we're doing, you take the derivative, first derivative, second to 0, solve, look at the first derivative for undefined, and look at the endpoints. Step 1, check to make sure that the f is continuous over a to b, find the critical numbers from a to b, evaluate f at the endpoints a and b, numbers found in step 2. The absolute max of f is the largest value found in step 3, and the absolute min is the smallest value found in step 3. Okay? So let's practice. Try this one. I'd like you to find all the extrema and label them. And then we'll find out if they maxes or mins. Maxes or mins. Absolute or local. Okay, so what you're going to find is your issue may be derivative, your issue may be factoring, or your issue may be graphing. Again, find all the extrema, make the table, graph it, label. Is it a local max, local min, absolute max, absolute min? Give it another minute. You can find out where the issues are. Is it the factoring, the derivative, the graph? Where are the issues? So let's see how we're doing. All right, so let's make sure we're very clear. If I say find the extrema, that should prompt you that there's three things we need to check. Three things we need to check. First thing, you take the first derivative, which is 3x squared minus 12x. 3x squared minus 12x. Set that equal to 0 and solve. If factoring is your problem, this is why we did Appendix A. This is why we did Chapter 1. This is why you took college algebra. Okay? Got to be good at factoring. You can pull out a 3x, which leaves you with x minus 4. 3x equals 0. We get x equals 0. X minus 4. Add 4, add 4. X equals 4. Did everybody get 0 and 4? Did everybody get 0 and 4? Again, if that factoring keeps on coming up, that's an issue. You could have used quadratic formula. A is 3, B is negative 12, C is 0. Questions there? Okay. Step 2. Look at the first derivative. Is there any place where we're dividing by 0? Anything can make it undefined? Do we have anything like that? No. And then 3, do we have any endpoints to consider? What are the endpoints? Negative 7, 7. So now we have 4 possible extrema. I don't know if they are or not. I have to check it to see if they are. But those should be the points that we're concerned with. Are we okay? So we make a table. The numbers I need to check are 0, 4, negative 7, and 7. Are we okay? Now, where do I plug it into? I plug it into the original. So I go to y equals, the original is x raised to the third minus 6x squared. I go to the table feature, 0, 4, negative 7, 7. Are we okay? Any questions up to this point? I need to check 0, 0. I need to check 4, comma, negative 32. I need to check negative 7, comma, negative 637. I need to check 7, comma, 49. Now, I will say that in the slides, they made a mistake. It's not supposed to be negative 7 to 7. It's negative 1 to 7, but we'll just use this. No problem at all. Okay? Now, if you need to see if it's a max or a min or what it is, I need an appropriate window. What will my x-axis be? That's it, negative 7 to 7. Why? That is a domain. Those are endpoints. Nothing exists before. Nothing exists afterwards. Okay? So negative 7 to 7. Now, what should my y be to cover these y's? How low do I need to go?
Negative 700.
Like negative 700. How high do I need to go?
100.
Maybe 100. Good call. So I'm going to go down to negative 700. And I'm going to go up to 100. Why? Because my domain says it goes from negative 7 to 7. And my y's require me to go down to negative 700 and up to 100. So when I go to window, my window is going to be negative 7 to 7, counting by ones, negative 700 to 100, counting by hundreds. When I hit graph of the original, that's what it looks like. So the points I'm concerned with are negative 7, 6, negative 637, 0, 0, 4, negative 32, and 749. Now that you have the graph, label what we have. Now that you have the graph, label what you have. I'll put it over here. With the graph now, label what you have. With the graph now, label what you have. Okay, so one at a time. What do we have at 0, 0? Local max. What do we have at 4, negative 32? Local min. What do we have at negative 7, negative 637? Absolute minimum. Absolute minimum. It's the lowest point in the entire graph. And what do we have at 7, 49? Absolute max. Okay? Stop there. We're going to do more examples, but stop there. That in a nutshell is 4.5.
In a nutshell.
In a nutshell. You know what that means? We've heard that expression?
No, yeah, I'm saying, like, there's still more?
No.
Oh.
That's pretty much it.
Oh, okay.
In summary. Yep.
So basically, like the domain for either
Or local. Yeah, it could be anything. The only thing we're saying is to find extrema, take the first derivative set equals 0. Those are possibles. Make sure, is there any number that makes the first derivative undefined? Those are possibles. And the domain of possibles. They don't have to be absolute. They could be local. They could be neither. We don't know what's going to happen. But generally, the endpoints are going to be a local or an absolute maximum.
And the endpoint is always going to be given.
Yeah. And if there are no endpoints given, you don't have to worry about this step. You should see if there are any, but if there are none. Like in the first, when we first did 4.1, there were no endpoints, but they will be given. If they are given, they're part of the consideration. If they're not given, then there are no endpoints. It just goes forever. And that's what gives the arrow up and the arrow down. It goes forever. Okay? So there's a little trick. I find it really essential. That's where we may have a difference here. How do you know if it's absolute or local? I would say graph it and look at it. That would be my answer. But there is a mathematical way of figuring it out. If you find the max or min and want to know if it's local or if it's absolute or local, you take the second derivative and plug it in. If you take that number into second derivative, and you can determine if it's a local max or local min using the second derivative. So these pictures kind of show what happens with the second derivative. If the second derivative is less than 0, you have a local maximum. If the second derivative is greater than 0, you have a local minimum. It's kind of opposite than what you would think. So this is saying if the second derivative is greater than 0, then that point is a local minimum. If the second derivative is less than 0, then that point is a local maximum. So we'll practice this. But if you plug into the second derivative and it's greater than 0 or less than 0, you can find out what it is. So theorem 3 in the second derivative test for absolute extreme on an interval says let f on the continuous on an interval from a to b with only one critical number from a to b. If the first derivative equals 0 and the second derivative is greater than 0, then you have an absolute minimum. If the first derivative is equal to 0 and the second derivative is less than 0, then you have an absolute maximum. Okay? So bottom line, second derivative greater than 0, you have an absolute min. Second derivative less than 0, you have an absolute max. That's the summary. I think it's nice to know. You may find it very useful. We'll see. Okay? So let's practice with this one, everything. Let's start from the top. We seem to want some good practice. I would like you to find the extrema of x plus 4 over x from 0 to infinity. Okay? First of all, to find the extrema, we need to take the first derivative. So what should I do with the original before I even try to take a derivative? Rewrite it. How would I rewrite it? X plus what? 4x to the negative 1. So that's the original. Now, I'm going to give you some time to work on it, but the endpoints is from 0 to infinity. So do I have any endpoints? Am I going to use both, one or none? I'm only going to use 0. Can I plug in infinity? I can't. So when you have this 0 to infinity, that's saying you just check 0. Okay? So go through this. You're going to find the algebra is a little bit harder, but you can do it. And then I'll add that second derivative test to show you that. Because something's going on there. So remember, all these are possible extremas, doesn't mean they are. I'm going to give you a couple of minutes just to get you started, and we'll go over it. But again, it goes back to derivatives, algebra, and graph. I'm worried about a whole bunch of other things. It's going to go back to that stuff. want to get you a head start. So if you're like, oh, I can't solve, oh, I'm stuck here, that's where you're gonna have problems, right? So let's take the first derivative. Derivative of 1x is 1. The derivative of 4x to the negative 1 would be negative 4x to the negative 2. Good so far? Yep.
Do you leave it like that, or do you put it in the back?
Well, let's talk about it. So I have to set it equal to 0. Can I solve for a negative exponent? Nope. So I'm going to have to change it anyways. So in order to solve, set equal to 0, this is going to be 1 minus 4 over x squared equals 0. If you do not know how to do that algebra, you're not able to find that point. You're not able to get the answer. Algebra, algebra, algebra. So how do you do that algebra? If it was me and I have a variable in the denominator, I would add 4 over x squared, add 4 over x squared, and I would get 1 equals 4 over x squared. Why does that work? What have I just created? I've just created a proportion. 1 is 1 over 1 equals 4 over x squared. How do you solve a proportion? Cross multiply. 1 times x squared is x squared. 1 times 4 is 4. X squared equals 4. Therefore, x is what? Is what? Is what? Positive or negative 2. Now, algebraically, we got 2 answers. We got x equals negative 2, x equals 2. Now, you could have also multiplied everything by x squared, cleared the fractions. There's other algebra ways of doing it. But does everybody see how I got negative 2 and 2? Are we okay? Let me remind you something. What did the domain say? The domain says the only thing that exists is 0 to infinity. 0 to infinity. So are both of those answers possible? Which one can I get rid of? Not because I didn't get it as an answer, because the domain says 0 to infinity. It only exists from 0 to infinity. Negative 2 doesn't fit in the domain. I only have one answer so far, which is 2. Are we okay? So that domain means those are the only answers I'm looking for. Good so far? 2. I look at the derivative, the first derivative, and yes, I'm going to simplify it. Is there a number that I could plug in that would make this undefined? What is that number? So that is what step 2 is all about. That's what step 2 is all about. What number makes the first derivative undefined? That could also be a possible extrema. That could also be a possible extrema. There's the first derivative. What number makes that undefined? 0 would make that undefined. And then the third step, look at the domain. Look at the endpoints. And my endpoints are 0 and infinity. What's the only number I can check? 0. So after all this work, what numbers am I going to go check? 0 and 2. And where am I going to plug it into? The original. So in my calculator, I'm going to type in my original. My original is x plus 4 divided by x. When I plug in 0, I get error. We'll talk about that. When I plug in 2, I get 4. What does error really mean? Undefined. So as far as local max, local min, do I have any? No. Remember, these are possible extrema. It doesn't mean they are. But something weird's going on at 0, which could be undefined. It could be an asymptote. Something's going on at 0. We'll go look at it later. But when I plug in 2, I get 4. So my question is, what do I have at 2, 4? And in order to see what I have at 2, 4, you have to graph it. So I'm going to give you a couple of minutes, not much, because number 1, you may have algebra issues. Number 2, you may have graphing issues. The domain was 0 to infinity. Try to figure out what that means. And then look at the y's to figure it out. So try to figure out an appropriate window without me doing it for you. And tell me, is it a local max, local min, absolute max, absolute min? what do we have at 2? We know there's nothing going on at 0, but what's going on at 2? Okay, so 0 to infinity. Ugh. I know I have to start at 0, but infinity means it goes on forever. So I'm going to look at my x's. I need to see 0 and 2. So how far out should I go? 5, 10, all those are great. Let's do 10, and I can always change it to 5, or as long as it's beyond 2, you're good. Looking at your y's, I need to see 4. So what should I go for my y's? Maybe 0 to 10. And again, you can always change your window, but remember the goal is to be able to see the point that I'm concerned with. And the point I'm concerned with is 2, 4. In this window, I'll be able to see 2, 4 clearly. Okay? So remember, y1 has my original, the window being 0 to 10, 0 counting by 2s, let's say, 0 to 10 counting by 2s. Hit graph. It's a good picture. And after getting that good picture, what do we have at 2, 4? What do we have at 2, 4? An absolute minimum. Are we okay? Now, we said it's an absolute minimum. We said it's an absolute minimum because when you plug in 2 and look at it, that is the lowest point in the entire graph. Are we okay? Now, they're adding, which I think is nice to know, but you may think it's essential, that if you take the second derivative, plug in the 2, that result will tell you if you have an absolute or if you have a absolute max or an absolute min. So I want you to find the second derivative and plug in 2. Find the second derivative and plug in 2. Find the second derivative and plug in 2. And again, I think this is nice to know. If you want to do that as a good check, I think it's good. I think once you see it, verify it, you're done. But this is a nice little extra. Take this. Sorry?
I thought you said the second derivative was only for local max, local min. There's a problem.
First derivative is how you find local max, local min.
Oh.
Second derivative is how you find concave up, concave down, and the inflection point. And also, it can check your max and min as an absolute.
Plus 4.
Yep, I just rewrote it.
1 plus 4.
That's the original. The first derivative will be 1 minus 4x to the negative 2. The second derivative will be what? Okay, so my second derivative is 8 over x to the third. Now, what they're saying is, if you take the 2, plug it into the second derivative, you get 8/8, which is 1. Are we okay? And again, I think nice to know. But if you take this, the number, which is 2, what we found, plug into the second derivative, since that number is greater than 0, you have an absolute minimum. If the result was less than 0, you would have an absolute maximum. Are we okay? It's just a way to verify, just like the sign chart. Remember I told you the sign chart wasn't my favorite, but it's a nice way to check what's going on. I think this is the same thing. This is good to check, but you have to remember, greater than 0 means it's an absolute min. Less than 0 is an absolute max. We okay? So going back to the slide real quick, we found our critical numbers. The only one that works is 2. If you take the 2, plug it into the second derivative, you get a result that's with 1, which is greater than 0. Therefore, you have an absolute min on the interval 0 to 3. Okay? And let's hope this one had sound.